When I was, it's 19, it's 2005. I'm going downstairs in my Marina Del Rey apartment in Los Angeles and going down my elevator to the parking garage. And I had just bought a new car. My company was doing pretty well. I could actually afford a car. And the elevator doors open, banana in hand, almost done eating that, my morning breakfast. And I'm walking up to my car and I see two guys sitting on the hood of my car. And I'm like, oh, I'm getting carjacked. And I walk up, and two more guys come up to my car, come up to me. And they say, Samy? I'm like, carjackers don't know your name. So I said, yeah. They say, Samy, we have a search warrant. And I'm like, oh my gosh, I'm 19. I have no idea what that means. I was watching a lot of 24, and on 24, they always say, show me the search warrant. I don't know if that's a real thing, but might as well, I'm only going to have this opportunity once, I hope. Show me the search warrant. And they just hand me a packet of papers. I'm like, okay. And then they start showing me badges. And it's Electronics Crime Task Force, Secret Service, Los Angeles District Attorney, and the California Highway Patrol. Probably because of my sweet car. And I'm thinking, okay, what are they here for? Because I was a teenager, little digital mischief, nothing too crazy, but that's how I spent every single day. What are they after me for? So I start reading this pamphlet of papers, and after a few pages, I see something labeled MySpace.com. Like, oh, they're here for this. 6 months prior, I was messing around on MySpace. I just wanted my profile to be a little cooler. And I found a way to execute JavaScript by fuzzing the browsers and bypassing some filters. I just wanted to be your friend. You visit my profile, you'd add me as a friend, and you'd add Sammy is my hero to your profile. It wasn't spreading, so I thought, well, if I can just make you add me as a friend and a hero, I can just copy the code to your profile. Well, the next morning, I figured out I should have hundreds of new friends by the end of the month. And I woke up to 10,000 new friends. That became exponential, 100,000 within a day, over 1 million new friends. Sammy is my hero on all these profiles. MySpace had to shut down. I didn't really know what to do. 6 months later, this is what happened. Secret Service at my door, a dozen agents with guns in my home, another dozen agents simultaneously at my office, at my company, all with guns, going through everything, taking everything I have, my computer, my Xbox, my iPod. And I went to court. After another 6 months, I ended up getting felony for computer hacking, and I wasn't allowed to touch a computer or the internet or MySpace.com. In case I was going to whistle into a payphone and somehow, which would be cool. Don't get me wrong, I probably would have tried, right? So no computers. Now, this was weird for me because I had spent my entire life on computers. I'd go to sleep, I'd wake up, I'd hop on IRC, I'd say hi to David Halton on our IRC network, StudNet, now defunct, I think, and work on projects all day. And it all started when I read an article in Frack, the e-zine, and it was Smashing the Stack for Fun and Profit in 1995, around 1995, by Aleph One. And this was how to do a buffer overflow. Now, I remember the simplest program in the world. He demonstrated the simplest program in the world. It said, what is your name? Enter your name, and you have a buffer of 100 bytes or so, and printf your name, hello, your name. And if you didn't check the bounds, you didn't do bounds checking, then you'd start overwriting other memory up your stack. Everything gets written in reverse onto the stack. And at some point, you start writing over pointers. And then you can change an instruction pointer, point to your own code at the beginning of your name, which can be shellcode, and then that takes over that computer. Now, if you make that shellcode, now if you connect that program to the internet and you make it accessible over a web protocol or internet protocol, well, now you can take over a computer over the internet, execute anything you want, any instruction, access everything, every piece of hardware. And that just blew my mind. That taught me, okay, things don't work the way we expect them to, or that we believe they do. I thought I knew how a computer worked. I was a pretty smart 11-year-old. I knew exactly how the computer worked. I had no concept of it, right? I still have no concept of it. So now I cannot touch a computer. So I can't play with these things that I'm playing with. So I thought, okay, well, how can I apply this stuff in the real world? And to me, the real world, reverse engineering to me is really taking a system and modifying it, understanding it in a way where you can maneuver it in a way that is not expected or intended. And I think that's what many of us do or are interested in. So how do we do that in real life? And I thought, okay, well, when I'm looking at a problem, if I'm trying to attack something, I'm looking at perhaps an expected output. What am I trying to control? And all of the inputs. What are all of the possible inputs? And I think the inputs are a place that we actually miss a lot of information. We're not always looking at what the different inputs are. So just as an example, we can take a look at a lock here. This is just a random lock. I haven't looked at this specifically, but if we take this lock, normally we'll probably see a pin pad on the front. So that would be an input, right? We can hit these buttons. Another input might be, typically, if you run out of battery, there will be some port so that you can, on the unsecured side, you can power it so that you're not locked out. Often there will be that battery port might also combine and have debug pins so that you can connect, if you're a developer or designer of the product, that you can also access it from the outside and extract information if you have enough privilege or authority. But if you keep looking and you break this down and you look at all the parts, then there are other potential inputs. If you take any piece of material, you take a metal and you heat it up, it will change its size. So temperature itself is an input, something that we don't always think about. We can see an example. If someone types in their PIN on the pad, then we can take a thermal camera and take a look at the heat signature right afterwards. So that would another example of a temperature input. If we look at the lock itself, maybe it's a solenoid. We think, how does a solenoid work? So let's say the expected output. Our desire might be to unlock that door so that we can go inside and get the whiskey and make ourselves an old-fashioned. So how do we get that lock to move? Well, the lock is ferrous, so that means you can use magnetism to pull that lock. Well, what actually pulls that lock in the first place? There's probably an electromagnet, right? The solenoid is an electromagnet. How does an electromagnet work? Well, it's a coil of wire, and you're putting current through it. And whenever you move current, whenever you move a charged particle relative to something else, there is a magnetic field that's perpendicular to it. So you're putting current through this loop of wire, and what's doing that? Well, there's a relay. And a relay itself also has a coil of wire, and that produces magnetic field that then flips a metal from going from normally closed to normally open, and then moves current from one place to another. How does that get triggered? Well, that gets triggered most likely by a transistor. How does that get triggered? Probably by the microcontroller. How does the microcontroller trigger all of that? Probably through the firmware that's written on. How does the firmware execute? Bootloader. Maybe there's boot ROM that executes that. What are all of the inputs that go into the firmware, into the bootloader? Most of that will be the pin pad. It might be the UART pins on the external. It might be power. Power is actually driving a lot of this. So all of these are areas that you can look to exploit. If you look at the debug port with power, well, now you might be able to access many of these locks will have UART going into the microcontroller. So maybe you can then extract the firmware and then look for a vulnerability. Some of those firmwares will have protection. We'll learn from many speakers here about breaking some of those protections, those bootloader protections, by performing something like clock glitching. But it's hard to access the clock, but you can access the power because there's power pins on the outside. So now you can perform power glitching from the outside to whatever the chip is inside the microcontroller, glitch it, extract the firmware, and then potentially extract the secret key. Now you can generate NFC cards. So if there's an NFC or RFID, these are more inputs into the system. Just the traces themselves on the circuit board. The circuit board is likely FR4, which is fiberglass. And now you have copper traces going everywhere, where any piece of metal is an antenna. All of these are different inputs. And I think there's some other really cool inputs that we can look at that we often don't look at, like pressure itself. Pressure is an input. If you have a piece of ice, we can think, okay, well, we can go warmer and it turns into water, or we can go warmer and we can turn it into gas. Well, you can also go colder back into water, colder back into ice, but then you can lower the pressure. And if you can lower the pressure and then you bring in heat, we can skip the water phase and go straight from ice to gas. So there are ways that we can then take advantage of that. And with that, what you can do is make Ben & Jerry's freeze-dried ice cream. So I really suggest this. If the lock has something like a motion sensor for unlocking from the inside, you can use something like air duster. The question is, how does a motion sensor work? Well, really, this is a passive infrared sensor. So when you're walking inside, you can get that canned air duster and then turn it upside down. So another exploitation, because a motion sensor isn't looking for motion, it's looking for a change in temperature. How do we know that? We can open one and we can look at what's inside. And there's an infrared sensor that's looking for thermal change. There's a Fresnel lens inside, a Fresnel lens on top. That's sort of that white thing that you see on the outside. But it's looking for a change in temperature. So how do we change the temperature? And we can do it through just the little nozzle between two doors. So I'm really interested in ground truth. What are the different inputs? And at the end of the day, we can think of inputs are all really just methods of transferring energy. Everything is energy. I hope you all have crystals at home. Crystals are very responsible for energy. Many of us have quartz crystals in most of our devices that resonate. This is surprisingly all true. One example of energy would be temperature. So I was at Easter, was a few weeks ago, a month ago or so, and it was a Greek Easter. This year, I guess Greek Easter fell on the same as our standard Easter. And at this party I went to, they handed out these eggs, and they were painted red. And this is a traditional Greek Easter game where you take your egg and you hit it against other people's eggs, and the winner gets a prize, of the coveted chocolate egg. I'm like, okay, like cool. So I took my egg and I hit somebody else's, beat them. Took my egg, hit somebody else's, beat them. Now, it doesn't actually matter who hits which direction. For every action, there is a equal and opposite reaction. But I had an old-fashioned in my hand, so, as they're explaining the rules, I put my egg in my old-fashioned. As it got to cool, it became stronger. Just like you take water, you can convert it to ice. If you take the colder something is, the stronger it will be. So temperature is a pretty cool attack vector. There's the famous cold boot attack. Cold boot attack. When you take your laptop, our drives are encrypted. Now, when you turn on your computer and you enter your password, Hunter12, then that will unwrap a secret key, and that secret key decrypts your hard drive. So what happens when you lock your computer and it's password protected? Well, if there are applications that are still running in the background, that means it's not really locked. It's only locked in the foreground for users accessing, let's say, the generic inputs like a keyboard or mouse. But if applications are running, then that means they're accessing the file system. If they're accessing the file system, they're accessing the hard drive. The hard drive cannot be encrypted for an application to actually execute any of that stuff, or to access any of that stuff, to read or write. So the secret key that decrypts the hard drive is still in memory. Once you've unlocked the computer once, no matter how many times you lock it again, unless you log out entirely or shut down. So a cold boot attack was an example of lowering the temperature of the RAM. Now, when you pull the RAM out, the secret key is in there, but it will it's volatile, so it'll immediately erase as you pull it out. But if you cool it down, RAM, specifically DRAM, there's a matrix of transistors and capacitors. The capacitors store the 1 or 0, really a higher voltage or lower voltage. And the transistors allow you to read and write that and then refresh that information. And if you cool it down, then it takes longer for a capacitor to leak and reach voltage equilibrium. So this gives you a few minutes to pull the RAM out of a laptop, put it in your own device, extract the memory, and extract the key. We saw the example using like an ATM pin pad just by looking at the thermal. Also, I was curious, with the passive infrared sensor here, we can actually see the difference between using a vape and using canned air duster. We can actually see the cool that blue spot is coolness. The vape did not produce any noticeable change in temperature. Another area that's really interesting is electromagnetism. So, it was a few years ago. I was enjoying an old-fashioned at a bar. I think I enjoyed one too many at this event, and I took my Uber home. And when I got home, I realized, I left my credit card at the bar. I should go drive back to the bar, but I don't know. I'm an engineer. I'm pretty lazy, so I just went online and requested a new credit card. I said I lost my card. It's just faster that way. And they sent me a card, and I thought, that's interesting. Like, a lot of the numbers look the same. So I wondered, okay, well, what's going on? So I got interested in credit cards a little bit, and I took my own credit card, and it has a mag stripe. I'm like, is that really magnetic? So I took my credit card and I dumped it in a bunch of iron oxide particles. You can see that here. And I pulled it out, and I saw data on the mag stripe. We can actually see the 1s and 0s with the naked eye and start extracting it. I realized afterward I put tape to cover on my credit card number. You can just read it from the bits. So, yeah, my bad. Side channel attack. Now, okay, no one uses mag stripes anymore, right? If you've ever tried to use your credit card, your chip card on a mag stripe reader, it says you must chip dip. So it's like, well, I had a debit card and that was mag stripe only. But like, how did that work? Like, how did it know that the debit card, we would allow that, but not my chip card? So I started looking at the other bits, and there's part of the mag stripe is called the service code. And this has things like, is this card international or national? Does this allow, cash extraction from an ATM? Is this a chip card? 1 or 0. Does this have a pin? 1 or 0. If you flip those bits, what happens? There's also integrity. So there's a checksum, but you can recalculate that. So to test this, I created a simple device called MagSpoof. It's just really a small AT-tiny AVR, which is like a small Arduino, driver, motor driver, and a coil of wire to produce an electromagnetic field. If we produce a current through a wire, then we produce a magnetic field. And then we can flip that back and forth with a driver. So if you flip back and forth, we can just simulate those 1s and 0s on the mag stripe. And I thought, okay, let me try taking my chip card, turning the 1 into a 0. Here we can actually see MagSpoof and testing it with my card. Now, what's really interesting was the reason I got interested in this was when I received my card, I realized a lot of the numbers were the same on the credit card. Not all of them, but a lot of them. I started looking into it. The last digit in any credit card is a check bit or a check byte. So you can actually calculate that based off the rest of the credit card. And the other numbers I found with this specific manufacturer, or driver was guessable. You can actually figure out what the next card in the sequence was. I was like, that's pretty interesting. So within MagSpoof, I put in my credit card, and then I hit my company up again. I said, oh, my card was stolen. So they disabled that number, and then they mailed me a new credit card. I hit the button on the MagSpoof, that went to the next sequence, and I used it while the credit card was in the mail getting shipped. So pretty interesting when we start looking at these things. Now, light is just another area of electromagnetism. Light is just a part of the spectrum. Here we can see Isaac Newton creating the cover for Pink Floyd. So when we go outside and we see the rainbow, the sun is behind us and there's water droplets in front of us, we'll see the rainbow. And if we look a little closer, what's really interesting about the rainbow, at least interesting to me, is the rainbow is only a tiny, tiny, tiny slice of the electromagnetic spectrum. So the rainbow is actually much bigger. Right? When you go outside and you see that band, well, you're just looking at a little slice. If you could see UV, you would see much more information. And if you looked at IR and higher, or longer wavelength, you would see much more. So the sky is actually full of light when there's a rainbow out. We only see a sliver. And here it actually looks pretty big, but it's really just a tiny sliver in that spectrum. So there's so many interesting areas of light that we can take advantage of. There's visible light. There was an amazing example using light commands where people were doing fault injection by pointing a laser at a MEMS microphone inside of things like an Alexa and being able to talk to it with light. There's ultraviolet light. Bunny and others have demonstrated using UV to reset fuses, such as security fuses, in order to then dump or extract firmware from a chip. Radio is another part of light. Radio and light are the same thing. Radio is just, we said at a certain frequency, we're arbitrarily calling this light on one side and this radio on the other, but they're the same. So it's nice to think about these things as similar. So there's a great quote that Major Malfunction Laurie has said, "In my experience, once data becomes invisible, something magical happens. They forget about security." And I find this true. Even when I can't see something, I don't really think about the security. Now, as I didn't have, as a Secret Service, they took my computer and my laptop. So now I'm basically listening to music with an iPod and these Dell speakers. And I recall that I had my laptop out and my phone was next to it, and I received a phone call. And did any of you ever hear the do-do-do-do-do-do-do-do? I was like, oh, that's pretty interesting. Normally, we might just ignore that, but I'm interested in inputs and outputs. I'm like, why are the speakers doing something when my phone is not even attached to it in any way? Right? It's not. So I thought, okay, well, maybe the cell tower is actually triggering this. Well, it's not the cell tower. It's actually your phone. Your phone is trying to communicate back with the cell tower. It has an amplifier inside, so it can receive that signal from the tower and then amplify it internally, a low noise amplifier. But when it's sending back out, if the tower doesn't hear it, then the cell phone will amplify and create stronger and stronger signal. That is then performing interference, electromagnetic interference on the speakers. The speakers themselves are just, you have your ground wire and your data wire, your voltage wire, and one for each channel for left and right, for example. Well, any piece of metal is an antenna. So if you have a strong enough electromagnetic field that's somewhat resonant, meaning the frequency is somewhat linked to the length of the antenna, if we treat it as a monopole antenna, you can inject information. So that means you can actually just play whatever audio you want on a speaker if you have a transmitter that's nearby, and you can calculate the resonant frequency, which you can do. So there's so many interesting attacks, like the Tempest attack from the NSA. Tempest was a paper came out in 85 explaining that you can take a CRT monitor, a cathode ray tube, and it has so many RF emanations that from an adjacent room, you can see what's going on the monitor. NSA was like, yeah, we've known that for the last 20 years, but, thanks for publishing. There was a great example of an attack maybe 5-10 years ago using a similar thing, but instead of doing an essentially side channel analysis, we can do fault injection. And we take a same antenna setup and we start injecting information. And what we're injecting is audio into wired headphones that have a microphone. If you ever look at the tip of one of these audio jacks, there's tip, ring, sleeve. There might just be a tip or sleeve. There might be a tip, ring, sleeve. If there's 4, that means left, right, ground, and microphone. What's cool here is that they're injecting onto all of these lines, and that means they're able to actually get the microphone line to have information. If you take electromagnetism and you hit metal, then it conducts electricity, the same as if you were actually generating audio on the microphone. So they started injecting audio onto people's microphones and started telling Siri what to do. Like, text this person hello. And I've been interested in things like how do we do things, if you take something like a wireless keyboard, what attacks do we have there? There have been some awesome attacks. Thorsten Schroeder and Max Moser did a great attack called KeySweeper. They built a sophisticated hardware device that was able to crack into certain keyboards. Travis Goodspeed, who is here, also improved this attack by using, instead of an expensive radio, he brought this down to using a $1 NRF24L01. He also found a really interesting way to take advantage of that. With that chip, you have to say what address you want to listen to information from, radio information. And he found that if you use a preamble, 010101, you'll just listen to everything because all packets begin with a preamble. So it would get confused, think it's the address that was part of a preamble was an address, and listen to everything. I further worked on this attack. So this keyboard, I won't name the vendor. It starts with M and ends in Microsoft. I wanted to see, can we inject? So I worked on this project called KeySweeper, which will allow you to both receive and inject. But I figure it'd be cool if it were small, that you could plug it in, and it would be sort of inconspicuous. So I took a small charger, USB charger, opened it up, one of those box chargers, opened it up, put it into a larger charger, and then put a small Arduino, an NRF24L01, and a phono board, a GSM board, so that it will then deliver everything, and also a battery, so that when someone pulls it out, it continues to run. It just turns off the LED on the outside. And when you plug it back in, it recharges. This was a fun project, and a few people then sent me this letter from the FBI. So the FBI had begun sending people a message about this wireless keystroke logger, about the KeySweeper, and to watch out for it. And I thought it was particularly interesting because they said, best practices to prevent a compromise could include, but are not limited to, office policies that address mobile device chargers. 1, limiting which outlets are available for device charging, knowing whose chargers are currently being used, and immediate removal of an unknown charger from the office facility. The charger doesn't matter. This is where I stuck it in. So next time, I'm going to use a banana. And that way, it's going to be limiting which bananas are available for eating, knowing whose bananas are currently being used, and immediate removal of an unknown banana from the office facility. So there's so many cool things we can do with radio and capacitance and inductance. And many of us might be familiar with the theremin. The theremin is a very cool tool, a musical device, created by Leon Theremin. Now, Leon Theremin made another device. It's called The Thing. And this was the first passive listening device that could respond. This is before RFID. It was essentially the birth of RFID. And what he did was he worked with the KGB, and he put this into a plaque that was then given to the U.S. ambassador as a gift. Now, there's no battery, there's no power supply, and no device ever existed without a battery or power supply of some sort before that had energy, other than mechanical devices. And he understood that you can power this remotely. So when you send power remotely, just like RFID, that will then power this microphone with an antenna that will backscatter so that they can listen. So quite a gift. Whenever the KGB gives you a gift, you just watch out. So it was 10, 15 years before the US actually realized that this thing was in there. And I've always been interested in these types of devices, like what other crazy things can we do? And laser microphones have always been pretty cool. A laser microphone doesn't need to really be a laser. It can just be a light-based microphone. And I first really heard about this at DEF CON 17, where these guys demonstrated sniffing keystrokes with lasers. So they would bounce a laser off a laptop, off a reflective portion of a laptop, and then pick up the reflection. And they would see the vibration. It was like, this is super cool. And they gave the schematic and the tools. So after some time, I thought, okay, this would be cool to actually try to build. I went ahead and attempted to build this. You always want to make sure that you have laser safety, wear appropriate goggles so that you protect your remaining good eye. Once you check for ANSI Z136.1. So I want to see, how can I improve the laser microphone? I built a basic one based off their schematic. I looked online. I looked at some MIT laser microphones, and I looked at every laser microphone schematic and information I could find out there. And I found that I built one, and it worked, and the audio quality sucked. It was like really, really bad. You can kind of make out what someone is saying if you point the laser on someone's window, and now you notice this big red dot on their window. And as sound is moving, sound is the movement of air. And now the air is pushing the window, and the window is making these minute vibrations, and that causes the reflection of the light to actually turn. There's another thing that's interesting about a window, a transparent window. We look at a window and we see maybe transparency. The more you turn to the side, the more it becomes reflective. And when you're at the side entirely, you actually have a perfect mirror at the very edge. Now, most windows, no matter what, will still reflect some light, and also it depends on the actual wavelength, the color of the light. We don't have any like perfectly reflecting or perfectly transmitting mediums. So I was thinking, okay, well, the audio quality sucks. Is there a way just to make it a little better? So I looked at, okay, how does, say, an FM radio work? Because that's all on the electromagnetic spectrum. And what we can do is we can tune to different stations. And those stations, FM is frequency modulation. So if we take frequency modulation, we're changing the frequency, and then we can tune to the frequency we want. So what if we do the same thing with the laser light? The laser light is already a wavelength. It is modulating itself. But what if you take the light and you turn it on and off and on and off, and you do that at high speed? I tested this. I used a laser driver with a bias T, and then I put a signal generator into it, and then I started modulating the laser at 1 megahertz. So it's moving at 1,000,000 times per second. Now, the way a laser microphone works is you have a photodiode picking up the receive signal, and then you're converting that back to audio. I mean, the photodiode converts to a voltage, you amplify it, and then you listen to some sound. Now, if we actually do that, well, what if we then put a bandpass, and then we can get rid of all of the other noise? Because virtually all of the noise is coming from stray light that's hitting your photodiode. And if we can just bandpass on that 1 megahertz, we can get rid of all of that noise. Here's a picture of the hardware side, the transmit side. It looks more complex than it is. It's really a big laser driver. It's just really big because it has Peltier coolers to cool the laser. That's not necessary. It's just what I had on hand. We have a collimating lens, and there's the diode here, the driver, and the RF mixer. And then I'm using an oscilloscope, which has a built-in signal generator. Usually when I'm hacking on stuff, I have smoke just because it looks way cooler. So you put your hoodie on, you let the smoke in the room. And normally on the receive side, you would just have a photodiode, and you'd go into something like your sound card, and then the sound card would do some amplification. Well, I need to do a little more here. For one, I want to use 2 photodiodes next to each other, so I'm actually picking up more information as the vibration is happening from the window. Then I want to bandpass around that filter. I want to bandpass. You need to then perform another amplification stage. Then you want to get rid of things that you don't care about, like audio under 20 hertz, or let's say over 20 kilohertz. So the receive side has a few more things. Happy to chat with people about more technical details if you'd like. But all of this analog circuitry was actually being kind of a pain for me, because now every little thing I'd have to modify my board. And now we're dealing with higher frequencies and this becomes complex. So I thought, man, it'd be really cool if I could just use some software like GNU Radio and deal with this. Oh wait, how can I just get this into my GNU Radio? Well, I took my USRP, the software-defined radio B210. I thought, all right, let me put it in this. The problem is the signal going to the photodiode is at 1 megahertz. And I can't actually, the minimum frequency for USRP B210 is 100 megahertz. So I need to get 1 megahertz to 100 megahertz. I got a ham it up converter that adds a 125 megahertz. So now I go photodiode to amplifier to ham it up, which brings it up to 126 megahertz into the USRP. And now you can route it to GNU Radio. Doesn't look suspicious at all. You can see all of the hardware here. This is on the transmit side, the receive side. Happy to chat later. And then I thought, okay, well, instead of a red light, it'd be cool if we didn't see it. So if we look at the rainbow, if we go outside and we look at the rainbow and we see red, well, right next to red is infrared, which we cannot see. Next to that are microwaves and Wi-Fi. So what if we do infrared? So I got this infrared camera and I took an infrared laser and I saw, okay, cool. On the right side, we can see, I have this dot and that's my infrared camera. And on the left, when the left square, I'm pointing, that's visible and we can't see it. But I wanted to see what it actually looks like. So with the infrared camera, I was pointing the laser at my laptop and, pushed, and I took some of that, an iron with steaming water. So I'm like laying on the ground with this iron, steaming it, and then I just started burning myself. So I have all these dots on me. And while I was doing all this tests, I thought this is actually really interesting. I have this monitor with the infrared camera. The infrared camera is now just showing me whatever's on the camera. And I had some music playing and I changed the song. I didn't like the song that was playing. So I pulled out my phone. I opened Spotify and as I unlocked my phone, I noticed this on the monitor, on the infrared monitor. I was like, wait, what are all these dots? And I found that the last app I had opened was the camera app on my iPhone. And the camera app apparently uses LiDAR to detect which camera should it use. So it is using LiDAR to see how far is the thing that is in focus, or at least in the camera frame, how far is that? And based off that distance, it will then decide which camera to use. It's a very cool feature. But now that we can see it, I started measuring it. I figured out what wavelength it was, how fast those dots are actually transmitting. And now I have a prototype device that tells you when someone's pointing their camera at you, even before they're recording. Because as soon as you get out of the camera app, it no longer is sending that LiDAR information. So these are ways that we can actually take advantage of information that we don't even know is often happening. At least I didn't know that. Some of the hardware I use the split cell photodiode for actually receiving. This is cool because there's actually 2 photodiodes inside. So you can get 2 signals and then you can see as things are moving between them. Oops, I just hit the wrong button over here. Okay. I did notice this hair in the photo. And then software, use GNU Radio. Most of these things are just variables. It's really just a couple of blocks to do all of this. You have your source. It's important that you have a high bit depth, analog to digital controller. As well as a decent enough sample rate. I also found I could use a Sally logic analyzer for this. A couple of blocks. We don't need to go over them, but happy to chat about them. We're really just taking our 126 megahertz, bringing it down to DC. We're then doing a bandpass filter around our 1 megahertz so that we just get our information. We block out all the noise. We demodulate because we are going at 1 megahertz. We want to demodulate that information and get back to the DC signal. Once we do that, we can just write to a file, and I have this beautiful audio. I can hear what's happening inside of a place at about an order of magnitude better. So with my laser microphone, I was getting about 300 hertz of decent signal. I could get to 3 kilohertz of signal. And I was thinking about this. I took this audio and I put in isotope RX just to clean it up a little. And I thought, okay, there have been some pretty cool attacks out there where people have used the audio of keystrokes to listen to what is happening. And while a keystroke doesn't reveal what key it is, the placement of a key on a keyboard tells you exactly where it is, if you know what they're typing, because the key is producing a unique sound. Just like hitting a drum in a different location will produce a different frequency. You can perform the same thing with a keyboard, a physical keyboard, or really any piece of material. Hitting it in different places produces different sounds. So what if we look at keystrokes? I found this tool called KeyTap3 by this guy, Giorgio. He likes big VimRC and he cannot lie. Okay, I agree. And the way the tool works is that it listens to the keyboard, to the keystrokes themselves, and it treats it as essentially like a substitution cipher. This is a Zodiac killer for those who know. He would write substitution ciphers and then send it to police regarding all the people he killed. And with a substitution cipher, that's like saying A is B and B is Q. And you can really just brute force, assuming you know the language that someone is. Where is that? 1, 0. I can't read the numbers, sorry. Thanks. I just got PRK eye surgery, so I really can't see anything. I just see a bunch of beautiful blobs in front of me. It's amazing. Here we can see the actual hardware setup. This was an example of pointing to my laptop through a window. Here's running some software just sped up a few X. So I'm taking the laser going through the window, hitting the laptop, taking the reflection, running through FFmpeg, run the audio to Isotope RX to clean up the audio, and then we can actually go from a typed signal to what they typed. You can see it's about 90%, 80% accurate here. And here we can see a waveform. Actually, we can probably can't hear this, but this is like an example of audio. So that is about how much you can get. That's about 3 kilohertz of sound. So that's an actual example using the laser microphone. Now, all of these are really just examples of inputs, right? Different inputs that we can look at, like sound and light and temperature, magnetism. And that's something that I want to continue looking at. So it was 4 years that I wasn't allowed to touch a computer. I wasn't allowed to touch the internet, and I wasn't allowed to touch MySpace.com. And since then, I've really been interested now in physics. So what else, if we take, I've learned so much from you guys, from side channel attacks, fault injection, looking at radio protocols and understanding. And as we dig deeper and deeper, you might look at a radio protocol and say, okay, well, this radio protocol is, let's say Bluetooth. And we can send these different Bluetooth packets or these GATT packets or advertisements. But then you can go down another layer and you can say, okay, well, it's really Gaussian frequency shift keying, which is just changing your frequency from 2.40 gigahertz to 2.4001 or whatever the offset is. And then we can look at, okay, well, there's Manchester encoding. That's how we encode the ones or zeros as a 01 or a 10. And then we can go lower, like what is 2.4 gigahertz, right? That is light. There's light on the electromagnetic spectrum. And I just wanted to go lower. Like, how can we keep looking at how this stuff works? When we take that circuit board, when we take that FR4, if we take a keyboard and it has all of these keys on it, well, all of those keys, a keyboard itself, a plastic keyboard from the M company that we don't know who it is an ABS shell. And the circuit board is FR4, that's fiberglass. And then there's all these traces. And those traces are metal, they're copper. And any piece of copper is an antenna. And if we measure the length of that antenna, we find the resonant frequency. What if we create a software-defined radio that injects at the different frequencies of each of those with a really tight Q, meaning a really tight bandwidth or wavelength? Well, now you'll start to inject DC onto a keyboard, even if it's a USB keyboard, right? A non-wired keyboard, you can inject current, and now that will talk to the microcontroller. Well, the AC signal is actually, RF is AC signal. Your keyboard is DC. You don't want to send a negative voltage to those pins. Fortunately, any keyboard is a scan matrix to save on GPIO pins, and they have diodes rectifying everything. So there's already diodes built into your keyboard so you can perform attacks like this. I took some looking at light and radio and trying to understand these better. I just went through Wikipedia. I'm like, what is light? And it's made of photons. I'm like, well, what's a photon? It's like sometimes it's a wave, sometimes it's a particle. This is an example of a double slit experiment I was doing in my living room. It's like, wait, I don't understand. So if light goes through these two slits, you actually get this interference pattern of dark and bright bands. There's a great Veritasum video where he shows an example of this. The same thing happens with water. If you hit water and you hit it with your fist, you create a round wave. If you have two dams and those dams are open, then two new waves propagate from those two openings, and now you get two new waves, and then they interfere with each other. And what's amazing is that if you take a single particle of light, a single photon, and you go through the double slit, you will also see an interference pattern. And that's because what's happening is now you have quantum superposition. You actually have the photon in two places, but it's not detectable in one place. Now, we say it's not detectable, but it is detectable because the fact that you saw it over here and not at the slit means that it must have interfered with itself. If it interfered with itself, that means that there was nothing blocking your path. If that's the case, then that means that you've learned information, you've gained information about a path that did not interact with light. And if we think about this, and there's many articles that you can read, I'm sure we all have academic subscriptions to places. You can look at things like Wikipedia or find articles online or research and learn about amazing experiments like this. The Ultra-Weidman bomb tester is actually very cool. This essentially demonstrates something called interaction-free measurement. And this is a new era of physics that we can perform today. Like actually today, you can go home, build an experiment, generate single particles of light, and start exploiting new properties of physics that we're not exploiting today, that often people like Google and IBM are doing inside of a quantum computer. And you can start doing things like interaction-free measurement, which means like you can create LiDAR or radar that is undetectable. You can create biomedical imaging that it does not ionize, let's say an X-ray that does not ionize living tissue. You can exploit these things. I've been building up, I just got an optical table. They delivered a 350-pound optical bench to my driveway. I then had to get like one of those forklift things to get it up. But without the computers, not having any computers just really taught me, okay, what are the inputs in the physical world and how can we take advantage of those in interesting ways? And I hope that some of you will start thinking about when you hear that you'll think, all right, instead of just saying, oh, that's annoying, like say, look, what is that and how does that work? And thank you so much for listening.
Thank you so much for the great talk.
Thank you.
We have time for some questions now. Are there any questions? Very well received talk then. Oh, there's one question.
Awesome.
Personal question, I guess.
Yes.
Where do you work now? What do you do?
Oh, good question. So I started a company 8 or 9 years ago with some friends. It's a physical access control company. So we created a new system using RFID cards. It was called OpenPath. We got acquired a few years ago. But instead of RFID cards, we used Bluetooth and we created a asymmetric cryptographic layer on top so that if your phone, which actually has the capability of doing asymmetric cryptography, unlike every RFID card that we use, which is all symmetric and broken, this would allow you to enter your building. It's for business and enterprise. And there's no secret keys stored in the readers, unlike every other reader out there, so that you can actually have proper asymmetric crypto. That was acquired a few years ago, but throughout that company, I really started getting interested in physics and started spending all of my free time really just reproducing experiments and saying like, okay, wow, what can I do? I did like the basic double slit experiment. I was like, well, this is just with the classical lights, with a laser. How did people were doing this 40 years ago with single photons. How did they do that? So I started just looking at the papers, reading them, not understanding any of the words. ChatGPT came out. It helped me understand a few of the words, and found, well, if these people were doing this 40 years ago, then I can just order a lot of this equipment myself used on eBay for much cheaper, and start actually reproducing the real thing. And I found that you can just sort of generate all of that yourself.
Thank you.
Thanks. Yes, over here. I still have one good remaining eye, so that's cool.
Yeah. In the spirit of hacking on deep physics, have you thought about at all exploring like the differences between bosons, hadrons, and fermions? I don't know.
I don't know the difference between those. Once I started reading about the double slit experiment, about this wave particle duality, so there were two things that really bothered me. One was that I thought everything was deterministic. Like I thought life was deterministic. I didn't go to school. I dropped out of high school. That was the extent of my science. It was like 10th grade science, so whatever that is. And once I learned that you can take a mirror, like a half mirror. So let's say we're wearing aviator sunglasses that are somewhat reflective, but clearly some light transmits. So let's say 50% of the light reflects, 50% of the light transmits through. Well, what happens when you take a single particle of light? Does it reflect or does it go through? And that question was like, wait, it's random. And that was the answer. That's what quantum physics says. I'm like, I don't understand. Everything in my life has been deterministic, and everything is random. I need to see this. And then the fact that something behaves differently over here just by something being over here. And even if you have a single photon detector, you detect nothing. You can detect absolutely nothing over here. You can only observe information over here to learn about this path. Those two things just got me stuck on light. But I'm sure you can do amazing things there.
All right, let's thank the speaker again.
Awesome. Thank you so much.